All right, so one thing that was previously alluded to was the most stable trans configuration of a peptide bond. And so I want to bring your attention to this model on the left-hand side here. So the left-hand side here shows our peptide bond highlighted. It's a little bit grayed out there. And I want to go ahead and put an X over all of the atoms that are basically within the same plane. Now, since they are in the same plane, that means that, this oxygen atom right here and hydrogen are basically going to stay, I hate to sound so redundant, but they're going to stay in the same plane from one another. It's not as if this peptide bond is going to allow for rotation so that the hydrogen is going to be in close proximity to this oxygen anytime soon. Instead, they're going to basically remain where they are. Now, what we have is this molecule that's very rigid within this peptide bond. Within this bond. Now, proteins are dynamic molecules, so there's going to be rotation, there's going to be movements, but the peptide bond is going to be very restricted and it's not going to move very much. So what we need to think about is there is rotation of the bonds surrounding both preceding and following the peptide bond, but the peptide bond itself, there's basically going to be no rotation. So there's rotation around the peptide bond, rotation around the peptide bond is not permitted due to those resonance structures. So it's resonance stabilized. It's highly rigid and restricted. Now, rotation around bonds connected to the alpha carbon is, however, permitted. So just to kind of give you a little bit of an update or refresher, I'm going to draw a peptide backbone. N, C, C, N, C, C. This is for a dipeptide. I'm going to cross out my peptide bond. Now, what this is saying is that rotation around bonds connected to the alpha carbon. Okay, so my alpha carbon is here's one, and here's another one. So what this means is this bond, you can have movement, and this bond, you can have movement. And if this was a peptide that continued on, well, you could have this bond. So basically, the bonds that precede and succeed the alpha carbon, you're going to have rotation. Now, with that said, those bonds have specific angle measures that they can rotate. The phi or phi angle around the alpha carbon, the amine nitrogen bond, so that would be this one right here, for example. This is your phi angle. Then the C to C bond is another way to describe what's known as the psi angle. Okay, now those are the two bonds that you're going to see that rotation. Now, with that said, again, if we've got this peptide going on, that's not going to rotation, but this one will. So these phi angles and these psi angles, they're going to rotate. Now, with that said, in a fully extended polypeptide, in a polypeptide that has been stretched out, then your phi and psi angle measures are going to be 180 degrees. Now, the organization around that peptide bond paired with the identity of the R groups determines the secondary structure of the protein. Now, keeping in mind, one of the things that I said about what stabilizes the secondary structure was I mentioned that it was backbone hydrogen bond interactions stabilize the secondary structure, and I stand by that. Now, with that in mind, do R groups influence structure of a protein? They absolutely do. But what stabilizes secondary structure is the backbone hydrogen bond interactions. So an R group can influence secondary structure, but it's not going to play a role in stabilizing it. I hope that doesn't sound too duplicitous or anything like that. Now, with that in mind, here's another perspective on a peptide bond. What this shows is two different planes about two different peptide bonds. And it's also showing my phi and psi angles. So these two planes are basically rotating opposite one another. And what they are going to have is they're going to have angle measurements between 0 to 180, but then they can also rotate from 0 to negative 180. So they have both 360-degree rotation, but it's a matter of is it going backwards or is it going forward? If it's going forward, it's going 0 to positive 180. If it's going so-called backwards, it would be negative 180, for instance. So with that said, these two planes, they can rotate opposite one another, and what they're going to do is they're going to rotate and find a stable configuration. And stable configuration, stable combination. Now, what this is showing is another perspective of these peptide bonds, which I'm going to highlight. I'm going to put an X on my peptide bonds. There's one. And then let's see. Here's another one. Here's another one. Here's another one. I always kind of think about these as individual pieces of paper that are connected at the points, at the tips of them. So I'll use these Post-it notes as an example. So each plane in the center of it is a peptide bond. So we're going to have rotation like this, or rotation like this, but this piece of paper is stabilized. The atoms within the peptide bond are stabilized as this piece of paper. So you're not going to have the peptide bond rotate like this, but instead those individual things are going to move. Now what that means is my phi angles and my psi angles, those are going to have unique measures. Now those are going to have measures that are stable or unstable. And those phi and psi angles, they're going to cause the molecule to rotate, or parts of the molecule to rotate, and they're going to kind of restrict different parts of the molecule. So some phi and psi combinations are very unfavorable because of steric crowding of the backbone atoms with other atoms in the backbone or those side chains. Now, some phi and psi combinations are much more favorable because of the chance to form favorable hydrogen bond interactions along that backbone. Now, this is a whole lot of, to me, it's very complicated and it's kind of abstract. But a way that this can be visualized is with a graph known as a Ramachandran plot. Now, this shows the favorable phi and psi angles that are found within a protein. This shows, in addition to that, common secondary structural elements, and it reveals regions of unusual backbone structures. So this graph right here, let me show you the x-axis. We've got a phi degree that ranges from negative 180 all the way to positive 180. We've got a psi measure that ranges from negative 180 all the way up to positive 180. Now, one thing to keep in mind with respect to this is kind of an average protein. This is basically an average peptide, kind of a randomly produced peptide, randomly positioned R groups. Here's what's going to shake out. This white region, basically the vast majority of it, well, you're not actually going to have any favorable angle combinations there. This blue region, on the other hand, that's where you're going to see some of those favorable interactions. And they're highlighted here with parallel beta sheets, collagen triple helix, for instance. That's a very unique peptide fold, or a fold of a protein that is unique to collagen. And that's going to have bond angles that are positive, around 170 for a psi angle and around -1, we'll call it -90 for a phi angle. The important part about this is to understand that this is kind of an average representation of a protein's favorable bond angles. The peptide bond does not move, but those phi and psi angles, they are going to increase, decrease, and they're going to find some kind of favorable combination or combinations that work out. Now, of course, you can design specific peptides or unique peptides that are going to form really kind of unique Ramachandran plots. But what this is showing is kind of an average, and it's showing rough ideas of where different structures are going to be found with respect to their bond angle combination. Now, this is all leading to, so going from primary structure to a secondary structure. So primary structure, arguably it's not that interesting in some respects. And the reason that it's not that interesting is because it's primarily focused on, it's primarily focused on, well, it's stabilized by covalent bonds. And once you know it, it's really kind of most interesting to ask the question about how do those R groups interact? What do those R groups do as they interact? And what are those going to lead to with respect to structures? So the secondary structure refers to local structures. There are two regular arrangements that are commonly found. They're known as the alpha helix and a beta sheet. These are both stabilized by backbone hydrogen bond interactions. A fundamental difference between them is their structure, but also the alpha helix is stabilized by hydrogen bonds between nearby residues. And whenever I say nearby, it would be something like amino acid number 1 in a peptide and amino acid number 5 in that same peptide. Now, the beta sheet is stabilized by hydrogen bonds between adjacent segments that may not be nearby. Okay, so what's our difference there? This could be between amino acid number 5 and amino acid number 327. Okay, so why does this still get that local designation if these amino acids could be separated very different from one another? Well, the reason is that they're smaller than the entire structure. These are small structures that lead to the tertiary structure of the protein. Now, one irregular arrangement to the polypeptide chain is referred to as a random coil. So basically, if you wanted to think about a 3D structure of a protein or a tertiary structure of a protein, it's a bunch of alpha helices, beta sheets, and random coils. Alpha helices and beta sheets can be organized in a very unique fashion with respect to it might be 3 alpha helices followed by a beta sheet. There's sort of patterns that are discussed in structural biology. But if there's kind of an amorphous shape to a polypeptide chain, that's a random coil. Okay, so the first of our two structures is known as the alpha helix. The alpha helix is a helical backbone which is held together by hydrogen bonds between the backbone amides of an N and N plus 4 amino acid. What does that mean? Well, what that means is amino acid, the N termini right here, amino acid number N, here's the 3 atoms that consist of the backbone, and then another amino acid, C termini, 4 amino acids away. Okay, so basically if you wanted to, I'll put X's to designate in the just kind of a linear fashion what this would look like is this right here. It's my N. Actually, I'm going to draw it like this. That's N. And then plus 4 will be plus 1, plus 2, plus 3, plus 4. There's that. Okay, so what we're going to have is an H bond between the backbone atoms of these 2 amino acids. Okay, now what I drew at the bottom is the linear representation. That's going to fold. It's going to make this cylindrical shape to it. Now this helix, a alpha helix, is a right-handed helix with a measure of 3.6 residues per turn. Okay, now to wrap your mind around that, well, if we have one complete rotation takes approximately 3.6 amino acids. So to basically form a circle of it, it takes about 3.6 amino acids. Now, the height of that is displayed right here. It is 5.4 angstroms. So an angstrom is smaller than a nanometer. Peptide bonds are roughly parallel with that helical axis. Side chains point out and are perpendicular with that helical axis. Now to go back for a second, instead of right-handed helix, okay? So the terminology right-handed helix implies that there's left-handed helix. There absolutely is. Now, how do you distinguish a right-handed helix from a left-handed helix? Well, another way that you could visualize it is use your thumb to align with that central axis, this cylinder tube that's in the middle of the axis. Then it's a right-handed helix if, when your fingers fold in, they are going the direction of this peptide backbone. And this one is, so going from left to right. Okay. Now, if you look at a left-handed helix, your thumb is positioned around the central chamber. Your fingers fold towards your palm, causing this to, and visualizing it as it's going up like such. Okay. So this is just a thing to keep in mind, because later on we'll talk about structural proteins. For instance, not helix. We'll talk about collagen and, well, we'll talk about collagen, keratin, and those can form left-handed helices. And those left-handed helices, they have slightly different properties. Okay, so alpha helix is a right-handed helix. It takes about 4 amino acids, 3.6, to complete one rotation of that helix. So if you started right here to get right here, so there we go, that's about 4 amino acids. That's a height of about 5.4 angstroms. And sorry, my hair is falling out onto my face. Okay, now the top-down view of an alpha helix, the inner diameter of that helix with outside chains is approximately 4.5 angstroms. Now, what that is that cylinder, that central cavity, is too small for anything to fit inside. The outer diameter of the helix with those side chains is approximately 10 to 12 angstroms. These happen to fit well in the major groove of double-stranded DNA. So a helical protein, an alpha helical protein, is going to very well bind to structural parts of double-stranded DNA. Amino acids number 1 and 8 align on top of each other very well. And what this is going to give is, since all of your R groups are protruding outward, that central chamber doesn't really have anything in it. So there's not really anything that can disrupt it. Now, the amino acids that are in that alpha helix, they are going to have an impact. And I kind of alluded to this with the R groups are going to influence, but they're not going to dictate the structure. And what I was meaning by that was that you will have some very small amino acids like alanine and leucine. These are amino acids that are hydrophobic, and they love to form alpha helices. Now, one amino acid that we've previously talked about, proline, acts as a helix breaker because the rotation around the N to C angle is impossible. Now let's think back to the R group for proline. If you remember NCC, there's my backbone. Our proline looks a little bit like this. Well, what do we have to say? We've got what would be our phi angle right here, N to C. And this is another way of looking at phi. We're not going to have any rotation there. So that proline has two kind of components that are going to make any sort of movement very difficult. So proline is very restrictive because the R group goes back to the N-termini. Glycine is an amino acid that is very, very small. And it's going to act on, or it's going to be basically too small to support any sort of rotation or basically it's too flexible. Now, attractive and repulsive forces or interactions between side chains of 3 to 4 amino acids will affect that formation. So what that means, if I go back for a second, if we have, let's say, a lysine right here and an aspartic acid right here, that's a strong stabilizing interaction. That combination is probably going to lead to this helical formation because that interaction is going to be stabilized and help stabilize the overall structure of this structural element or this part of the protein. Now, we have this thing called a helical dipole. The peptide bond has a strong dipole moment, a carbonyl negative and amide positive end. All peptide bonds in the alpha helix have a similar orientation, and the alpha helix has a large macroscopic dipole moment that is enhanced by unpaired amides and carbonyls near the end of that helix. So the negatively charged residues often occur near the positive end of that helix dipole. So here's another representation of the peptide bonds that make up a alpha helix. So what we have is, or what I want to draw your attention to, is these guys right here. This is our network of hydrogen bonds, and here we've got, our network of hydrogen bonds here, here, and here, that are going to stabilize the structure. Sorry, disregard those guys. But it's this network of hydrogen bonds that are going to help position these peptide bonds and put these R groups on the outside of the overall structure. Our next secondary structural element, known as a beta sheet. The planarity of the peptide bond and tetrahedral geometry of the alpha carbon create a pleated sheet-like structure. Now, the sheet-like arrangement of the backbone is held together by hydrogen bonds between the backbone amides on different strands. Side chains protrude from the sheet, alternating in an up and down direction. Now, this is different from our alpha helix because the alpha helix, basically all the R groups are protruding outward. Whereas as we dig into a beta sheet, well, these side chains are going to be above or below, in which case they are ripe for interaction with things nearby, which could destabilize that overall structure. Now, when you look at the bottom here, what we have basically is a polypeptide leading from N termini to C termini. Now, this is one strand of a beta sheet. Beta sheets like to form structures known as anti-parallel and parallel beta sheets, or they form these two different configurations. When you have multiple beta sheets or multiple strands of a beta sheet that align with one another. Multiple beta strand interactions are called sheets. So sheets are held together by hydrogen bonding of the amide and carbonyl groups of the peptide bond from opposite strands. There are two major orientations of beta sheets that are determined by the directionality of the strands within. So parallel sheets have strands that are oriented in the same direction. Anti-parallel strands have strands that are in opposite directions. Parallel beta sheets, the hydrogen bond strands run in the same direction. Notice here's our N to C, N to C, and finally N to C. What I want you to notice about this is this right here, this right here, this right here, and so on. These are our hydrogen bonds. And earlier this semester, we talked about strengths of hydrogen bonds. And you can see at the top of the slide that it shows that our hydrogen bonds are described as weaker. Well, what are they weaker than? Well, they're weaker than these hydrogen bonds right here, where we have a strand N to C, and then another one, N to C, another one, N to C. These are going in opposite directions. So here we have our anti-parallel beta sheets. And this, to me, has always been kind of a tough thing to visualize. And I'm going to jump back to the parallel beta sheets in just a moment. But I think it's important to highlight which atoms we're talking about. So here's a nitrogen. Here's our alpha carbon, carbonyl carbon, nitrogen, alpha carbon with an R group, nitrogen. The blue balls are our nitrogens. And so we have this going from the N to C termini, and this is all in one polypeptide. So you might be thinking, well, C termini, I thought C termini was the end. Well, it is, but you could look at any peptide bond and identify the end of that peptide bond and the C end of that peptide bond. So I always kind of imagine that this basically loops down like that in a somewhat continuous form. So we've got our N termini here going down to C, C going to the N, and here is the one termini of that, or the one C termini of that complete polypeptide. Now, if we go back, okay, how do we do this with or how do we get a parallel beta sheet? Well, one way that you could think about it and visualize a polypeptide is N, and basically at the end of the day, we want something that looks like this, where two strands are in close proximity to one another. They can hydrogen bond with one another. Well, in order to accomplish that, going in that same direction, we have to have something that looks like this. This is the one C termini of that overall polypeptide. And arguably, this is the N-terminal portion of this end of this polypeptide chain. Okay, so this gets multiple parts of one polypeptide going in the same direction. So as you can see, it can get kind of complicated where we have multiple parts. So we could have something like this, and I hope I'm not recklessly ambitious with this, but we could have something like this, almost like a concentric circle situation. There's our C. So these are all portions of one polypeptide that are going in the N to C direction. So at the end of the day, the anti-parallel beta sheets are our stronger ones because our hydrogen bonds are directly, or they are straight. They're not strained. They are not at an angle or anything like that. Now, our anti-parallel beta sheets, as the stronger ones, are going to have our R groups protruding up and down from those sheets. The last kind of component or last part of alpha helices versus beta sheets is what's known as a beta turn. These occur frequently whenever strands of beta sheets change direction. Now, if we go back over here, this would be considered a beta turn. This could be considered a beta turn. So the turn is stabilized by hydrogen bond from carbonyl oxygen to amide proton, 3 residues down from the sequence. Proline in position 2 or glycine in position 3 are common in beta turns. So that's kind of interesting. We previously talked about, well, proline and glycine were amino acids that made secondary structures kind of unfavorable. But in some instances, in the case of a beta turn, proline's rigidity and glycine's like far too flexibility are what actually make that structure happen. Now, a visual of that. Here again, you always want to position yourself, or you want to visualize, where's my nitrogen? Here's my nitrogen, alpha carbon, C termini. Here is a peptide bond, nitrogen, C alpha, and so on. Here in position number 2 for a type 1 beta turn, you have a proline. And then in type 2 beta turn, in position number 3, you have a glycine residue. So glycine and proline, unfavorable for alpha helices, but great for beta turns. And therefore, they're great for beta sheets because they help go from one strand to another strand. All right, well, that's going to wrap up the material for exam number 1. And so I'm going to go ahead and stop my share and end my slideshow. So this exam, the volume of material that it covers, it's got a pretty good stretch and a good range of material. like I've said a couple of times, it's very important that you know your amino acid structures. I'm going to share the Actually, I'm going to go ahead and stop this. I'm going to make a separate video.